Hi there, I am Daniel Woody, and I am a statistical software scientist at Berry Consultants, where I work on building software products for clinical trial statistics. I specifically support ADDPLAN, our adaptive design planner, and today I'm going to talk about multi-arm, multi-stage designs, or clinical trials with multiple treatments and multiple interims. The agenda for today's talk is going over what is a MAMS design, or the multi-arm, multi-stage design. What can ADDPLAN do, specifically as it relates to designing, simulating, and analyzing data? Lastly, we'll take a look at a case study or a high-level overview of creating a design, simulating options, and analyzing data. To answer the question, what is a MAMS design? It's a multi-arm, multi-stage design in which you have both multiple treatments, multiple looks at the data. The benefit is that you gain operational efficiencies by using the same trial infrastructure to evaluate multiple treatments, and the added interims enable the opportunity to make faster decisions. The statistical cost of both of these choices is losing some alpha and power at both the interims and the treatments. So what can ADDPLAN do? So ADDPLAN has multiple modules. It has a module for dose escalation, has a base module for doing common group sequential designs, has a multiple comparison module, and it has MCP mod, which combines multiple comparisons and modeling, and it has a patient enrichment module. Today we're going to be taking a look at the multiple comparison module, which has additional features for more than 2 treatments in a simulation and analysis. Again, to take a look at the different components for each of these modules, we have a design option, a simulation option, and an analysis option. For the design option, you can answer questions like, how many patients should I enroll? What is my type 1 error and power? For the simulation options, you can take a look at, what is my expected sample size given some probability for stopping early? What effect does conditional power have on design? For analysis, you can say, I have some data. What is my p-value? Or should I adjust my sample size based on interim results and power constraints? For the case study, let's consider a clinical trial in which 2 novel compounds or treatments are compared to the existing standard of care or control for non-small cell lung cancer. The primary endpoint is mean improvement, in which a treatment effect of 0.5 is assumed with a standard deviation of 1. The trial significance level is set at one side and alpha equals 0.025, and power set to 0.8. We will do 2 interims plus a final analysis equally spaced. Early stopping at either the first or second interim for efficacy should be possible, for which the O'Brien and Fleming boundary is selected. So first we're going to take a look at the design option for this example. Specifically, using these constraints, we will determine the following. What are the cutoffs for test statistics, and how much alpha is spent at each interim? I should let you guys know it is currently not available to do sample size calculation in the design context. Instead, we will get these answers from a design panel within the analysis option. So pulling up ADDPLAN, you'll want to create a new frame. And on the statistical procedure, we're going to select multiple comparisons. The data type will be means, and again, you'll see the design option is not available. Instead, we'll need to go to the analysis tab to get the cutoffs and alpha spent at each interim. So on the right side, we'll input the details of the trial. So we have 3 stages. We have 3 treatment arms. That's 2 treatments and 1 control. The significance level is set to 0.025. And for the group sequential design options, we have for stage 1, 1/3 of the information will be available. Stage 2, 2/3, and stage 3 will have a complete set of data. For the boundaries, we're using O'Brien and Fleming again. There's options for stopping for futility, but for this trial, we will not be exploring that. For data input, we will be entering the data per stage, unknown variances, and pooling variances across each of the treatments. For sample size options, again, we'll explore this more later when we're going over the analysis piece, but for now we'll just set conditional power for next stage to 80%. We'll be entering analysis data here, I'm just going to put 20 for each treatment, and the control for the means. I will just input some fake options here. And what we really want, you will see, is not driven by any of this, but it's these cutoff points. So boundary for rejecting the null hypothesis, that's stage 1, 2, and 3, which is 3.4711, 2.4544, 2.004. And then if you want to take a look at the alpha spent for each, it's 0.0003, 0.0072, and 0.025. So coming back to the example walkthrough, we can answer these questions. What are the cutoffs for the test statistics, and how much alpha is spent at each interim? And the main thing that's driving these is actually the alpha constraints and the information rate set for each interim. Now let's do a simulation. With a simulation and ADDPLAN, you can run a trial, let's say 1,000 times. You can set up automatic decision rules based on expected virtual responses. The big thing that people explore is sample size reassessment. Using the same design constraints from earlier, let's explore a few questions. The simulation walkthrough. So we're going to take a look at the sample size for the same trial with overall conditional power at 80% and sample size recalculation at each interim. We'll also take a look at what is the probability we end the trial at interim 1. What about interim 2? Additionally, what if we change the power constraint? What if instead we update conditional power for each interim? How will the answers change for each of these questions? So again, we'll open up ADDPLAN, create a new frame, and instead of analysis, we'll select simulation. So for the computation options, we have 3 stages, we have 3 treatment arms, that's 2 treatments and a control. Significance level set to 0.025, our variance is unknown. For the, and we'll set our seed on this screen to 1. For the group sequential design options, we have a uniform information rate or equally spaced information rates for stage 1, 2, and 3. And again, we're using the O'Brien and Fleming design. We will not be stopping for futility. And here we will take a look at the different treatment options to explore in the simulation. So placebo effect will be 0, max effect will be 1, we'll set the drifts to 2, standard deviation to 1, and linear. So for this, we'll actually set this to 3. And then for selection rules, we'll select the best treatment arm. And for sample size options, again, we have to set the sample size from the beginning to 20 for stage 1. You also have options for adjusting the allocation to the control arm, which we will just make it constant over each of the stages. And then you have options for doing sample size recalculation or no sample size recalculation. We'll be doing sample size recalculation, and we'll make it conditional on overall power, set to 80%. Observed effect means we'll be using the data to do our sample size recalculation, and we'll be doing the recalculation at each interim. Once everything is put in here, we can run simulate. And now what you see, each row is actually each of the effect sizes. So when it's set to 0, this is the null scenario. When it's set to 0.5, this is one of the alternative scenarios. And when it's set to 1, that's another alternative scenario. In this case, let's take a look at 0.5. That's what we expect one of our treatments to be. So the probability of rejecting at least 1 is 0.816. And the probability that we're rejecting the effective one is 0.816. Again, if we're taking a look at the probability for stopping at stage 1, stage 2, or stage 3, for the alternative effect of 0.5, the values we get is 0.023, 0.346, and 0.631. When we're looking at the average sample size for 0.5, we get the total of 181.442, or for stage 1, it's 60, for stage 2, 67.586, and stage 3, 53.856. Now that we have those values, we can come over here, and instead of doing the overall conditional power, instead we might want to take a look at the next stage power. So we can clear our results and we can run the simulation again. So for this, we get, again, the top row is the null scenario. Middle row is the one we're interested in, which is 0.5 for the alternative. And then the third row is a more extreme case of having a max effect of 1. So for 0.5, the average expected sample size is 201.922. For stage 1, it's 60. For stage 2, it's close to 100. And for stage 3, it's 42.254. When we're looking at the early stopping results, again for 0.5, the probability of stopping at stage 1 is 0.026. Probability of stopping at stage 2 is 0.528. And the probability of stopping at stage 3 is 0.446. Alrighty, so that answers these questions for the simulation walkthrough. Last, we're going to take a look at analyzing some data. So for this scenario, you've completed your first interim with 60 total subjects, 20 to each treatment and 20 to control. The mean improvement for control is 0.5, where the mean improvement for treatment 1 is 0.75 and treatment 2 is 1.2. The standard deviation for control is 0.85 and the standard deviation for each of the treatment groups is 1.25. With that interim data, we're now going to take a look at what should I allocate for interim 2 based on an overall power condition of 80%. The second question will be, how does this change if I make the power conditional on the next interim? So there's a lot of details here, but first we're going to come back to ADDPLAN, we're going to create a new frame, and instead of doing simulation, we're going to run an analysis. And again, I'll set this up so we have 3 stages, 3 treatment arms. We have each of these values. We're going to use the defaults. Again, for the group sequential design options, we have equally spaced interims across the 3 stages. We're using O'Brien and Fleming cutoffs, and we will not be stopping for futility. There's nothing that's going to change on the Further Options tab. We're going to enter the data at each stage. We don't know our variance. And when we do get the data, we're going to calculate the overall pooled variance. And the first one we're going to take a look at is the conditional power, or when it's the overall conditional power set to 80. Alrighty. So for each of these, we have 20 subjects in control and the 2 treatments. The mean effect for control was 0.5, for control 0.75 for treatment 1 and 1.2 for treatment 2. The standard deviation is 0.85 for the control and 1.25 for the 2 treatments. Now that we have our data inputted, we can now compute values to take a look at for reassessing the sample size for stage 2. So given the design constraints, so for each of the interims, for looking at the alternative scenario of control versus treatment 1, what you see is that you'd need to allocate 143 for each of the treatments across the next 2 interims. for treatment 2, which has a larger effect size, what you see is 10.6758 for control and treatment 2 across each of the 2 interims. And now, if instead of doing overall conditional power, we want to instead condition power for the next stage, let's clear the results. We have our data stored, and we'll say conditional power for the next stage set to 80% in compute. Again, for this, we can take a look at the table for stage 1 and what they're recommending to allocate for the next interim. And what you see from this is a very aggressive reallocation for interim 2. So for comparing the small effect size of treatment 1 versus control, it's looking like 478.8731. And for looking at treatment 2 compared to control, it's 34.4833. Alrighty, and here's the answers, just if you need to take a look at that for each of these 2 scenarios. In summary, ADDPLAN can be used to design, simulate, and analyze multi-arm, multi-stage designs. The design components can be found in the simulation module, where you can find test statistic cutoffs and alpha spent at each interim. With simulation, you can explore conditional power and sample size reassessment approaches to further tune your design. With analysis, you can calculate p-values as well as power and sample size reassessment to tune a trial that's in progress. I hope that was helpful. Thank you for watching.